Great pleasure to have here today and every day, Nadine Soliman. She did her PhD in Caltech, then she got the Hubble Fellowship, and she moved to the IS, and she will tell us about microphysics methods. Yeah.
Thanks, everyone. I feel like everyone in this room knows who I am. In case you haven't, I'm Nadine. And yeah, so today I'm going to be talking about which microphysics really we should care about when we're trying to model systems like galaxies and star-forming regions. And I'm going to try to make the case for why dust dynamics is one of those relevant microphysics that we should care. So to first start from very, very large scales. So this is galaxy NGC 1512. And it spans tens of thousands of parsecs across, right? And we can slowly begin to zoom in. And if we zoom in on a particular patch, we'd probably see a bunch of individual stars. This is a picture of a planetary nebula that is sort of ejecting large amounts of heat, radiation, and most importantly for me, a lot of fresh dust. And if we go all the way down to the microscales, this is when we actually begin to see astrophysical dust grains. And what do I mean by dust grains? Astrophysical dust is essentially just the solid state of the interstellar medium. It is particulates that are made of carbon and silicates, and they vary in size from nanometers to several microns or millimeters. And they sort of comprise about 1% of the interstellar medium by mass. And throughout this talk, I sort of want to say why this very small particle that isn't that abundant actually matters for how galaxies on this scale evolve. So why should we care about dust? Yes?
What are the other scales in the ISM? So this is 1%. What is, in your definition of grain sizes, what is the rest?
Oh,
because you took nanometers to millimeters, this is 1%.
Yes.
Okay, what is the rest?
So the rest is mostly like gas.
Less than nanometer?
Less than nanometer would probably be like molecules, is if like approximately. So I'm saying if you make some cutoff that.
So gas is a state of matter.
Yes.
But what are the sizes of particles of gas, which is not between 1 nanometer to millimeters? So
the state of.
What differs the dust definition? So you took 6 orders of magnitude of size to define dust. Nanometer to millimeters. You say this is 1%. The other is gas. What scale of size is this other 99% of matter in the ISM?
Mostly just below like size-wise, below nanometers. Yes. All right. So what does dust actually do? So one very obvious effect is it affects how radiation is processed. So dust sort of takes this image that was taken by Hubble of this galaxy, and then if we sort of put our IR glasses on, which is JWST, the galaxy starts to look like this. So all the dark lanes that were sort of obscured in the previous image are now sort of bright in the IR as the dust absorbs UV and optical and then re-emits it in the infrared. So it affects how light travels through galaxies. It also changes the thermodynamics. So dust is one of the main sources of both heat and one of the main coolants in the interstellar medium, depending on the regime that you are in. So it also affects and regulates the temperature of the gas. It absorbs photon momentum and can launch winds and change the dynamics of different regions. And lastly, it's a very important component of chemistry because it acts as a catalyst for a lot of molecular reactions that happen on the surfaces of dust grains. So for example, molecular hydrogen is one of these processes that mostly proceeds on the surfaces of dust grains. And essentially it is because dust is involved in all these different processes that we really actually care about it. And all these processes depend on the exact properties of the dust that you have, right? So we can sort of categorize these properties into two main properties that we really care about. One is the dust to gas mass ratio. So just how much dust do we actually have in the system? The second is how large is this dust? So what is the grain size distribution that we have? So do we have mostly fine grains or do we have larger grains? And what this sort of encodes is the surface area that we have for all of these reactions to proceed on. So this is just total mass and this is the surface area. And using these two parameters, we could sort of now make approximations on how we can now model the dust and how it interacts with these different processes. And what people usually make is that they assume that the dust to gas mass ratio is constant everywhere in the galaxy. It does not vary spatially. And the second approximation is that the grain size distribution that you have in one place is the same as everywhere else in the galaxy as well. So you sort of have one grain size distribution everywhere as a function of both space and redshift. And this approximation is roughly okay, but it changes depending on the system that you're in.
When you say this is a typical assumption, in what context? In simulating things or observing external galaxies?
Both. So when you're like simulating a system, people usually assume that the dust doesn't move. So they assume that it's fluid to the gas, which is roughly the constant dust to gas ratio. And if you're looking at some like observing something, that you're usually extincting it with some assumed grain size distribution. But it depends on the exact
Probably post-processing simulations as well.
Or to like get a dust mass or to get a gas mass. So if you're observing the dust, for example, to get a gas mass out of it, you need some relation between the dust and the gas. So this is sort of where these assumptions came in.
Do you have also collisions, coagulation, and it breaks together, or is it for that? Okay.
This is a great point. A lot of people.
You said this number is basically assumed fixed?
Yes, it's assumed fixed.
This distribution is assumed fixed.
Fixed, yes.
But is it that fixed thing itself depends on the mass of the galaxy or the size or something? So one number for all possible galaxies?
Exactly.
Okay.
So that is, thank you for motivating my and
What do you actually mean by breakdown? What did people try to answer before some assumptions broke down? What is the question that people try to answer?
So essentially so it depends. So if you look at the grain size distribution, for example, the way
Observation?
yes.
Okay.
So if you look at different galaxies, you could see different extinction slopes, and that slope of like how extinction varies with wavelength tells you something about the species that are extinct. And that tells you the sizes of the size of the grains depend on which wavelengths they can extinct better or less. And if you observe different extinctions, different galaxies, that tells you that you're probably observing something that is varying in the grain size distribution. Or for example, if you see a region that is very dusty, so if you look at like H2 regions, you see a lot of variations in this ratio, for example.
So these are new observations that broke previous assumptions? Because why did people assume that the grain size distribution was constant? What observation led to that assumption?
So the reason you would assume it's constant is you need to make some assumption about the grain size distribution.
In order to explain what?
Huh?
In order to explain what?
In order to explain the extinction, mostly. So people were looking at the extinctions nearby from the diffuse interstellar medium. And from there, you can make bounds on the total mass of dust that you have and the size that it would need to match that observation. And we can't, you don't have as well observations for other regions. So you have to sort of use that same model for different galaxies that are further out, where you don't have as much resolution, for example, to resolve these things. And then once you put that in, then some of the stuff you could get out is not always very accurate. But sort of physically, we know that these things have to vary. So the reason is sort of dust and gas are not the same thing. Different forces apply on these two different species. So like dust is a lot more coupled to radiation than the gases. It's also charged, so it can couple to the magnetic fields differently than the ions or a mostly neutral gas. And from turbulence, you could sort of concentrate dust into different regions. So we know, and like if you go, for example, into the protoplanetary disk community, then that is a community that sort of relies on the fact that this ratio isn't fixed because you need to sort of concentrate dust in different regions. So you have these sort of forces that act on your dust that tell us that this approximation cannot hold in every environment. And sort of similarly for the grain size distribution approximation, we have all these models for what actually sets the size of a solid particle that is suspended in a gas. So like this depends on temperature, which sort of tells you how fast things move or how fast things collide with your dust particles. There's also the density. So if you're in a nice dense environment, you're more likely to collide with other particles, for example. You could stick together and form larger grains. You could also collide at very high velocity. And then that sort of high velocity collisions leads to grain shattering, which is roughly dust particles hitting each other. And instead of sticking together, they're too high of a velocity and they just break apart. So sort of from these arguments, we know that these assumptions also have to break down depending on. So from these sort of motivations, we wanted to.
Just a very quick naive question, just because of this picture, it looks, incredibly spherical. Is that the typical kind of shape, or would you say that's atypical and they're actually a lot more?
It's quite atypical. This is sort of a sample so it's a particularly nice looking sample that is easy to show on a slide without looking too wobbly. Yes, they come in all sorts of shapes and sizes and
as a function of size as well.
Yeah, and environment and like the conditions that they sort of.
What do you mean they come? What do you mean they come? I don't know.
So this is just actually sampled from space. So there are all these instruments that have like essentially like a dust like catcher. And we see if dust grains sort of fall in and then we collect them back. And we could observe some properties about this particular like solar neighborhood dust. Okay, so now that we know these assumptions can break down, we want to try to see, can we model all these forces on the dust grains and vary some of these assumptions to now see what actually happens in our simulations, and from there sort of infer what could be possibly seen in observations. So how do we model a dust grain, right? So now I have my dust grain. The first thing that I do is we use a superparticle method to model these dust grains, which is saying that I can't model every single dust grain in a galaxy. So I have each particle is representative of some ensemble of particles of similar properties. And for this particle, we sample from some given arbitrary grain size distribution to give it some size. And once we have size, we can give it density, so it has mass. And depending on the environment that it's in, we can compute the net charge that will be on the screen.
Question. So what is this distribution that you are sampling from?
So we're sampling from what is called an MRN distribution. This is the distribution of grains that you see in the diffuse interstellar medium. But it's very, very close to the distribution you would expect from a cascade of collisions. So particles that have their sizes set by collision.
Second question, what do you assume about porosity? I mean, do you have any cavities or just swish?
So we assume perfectly swished dust grains, but there's a lot of modeling right now that's going on to take into account porosity, because that changes a lot of the properties of these grains. All right, so now I sort of have a very simplistic model of what a dust grain does, but because I sample from a grain size distribution, just wanted to sort of clarify that we have in these simulations particles that correspond to different grain sizes. So you could check how different sizes sort of behave and interact with the gas. And once we have our dust particle, then we just integrate its trajectory in an environment so we can compute the effect of forces like radiation pressure, gravity, Lorentz forces, drag that will then couple it back to the gas, and an equal and opposite drag back reaction force that it will now exert back on the gas. So this is sort of our dust model. And now we could sort of begin to ask certain questions. So if I now take my dust model, I want to put it in some environment. I want to ask, what does this microphysics that we just added in, how would that change how macroscopic astrophysical environment behave? So for that, today I'm going to talk about two main environments. I'm going to talk about star-forming regions, which is going to be most of this talk, and towards the end, I'll quickly talk about the effect of charged dust grains on cosmic magnetism and generating magnetic fields with these dust grains. So start with star-forming regions. What the simulations that we use are these star-forged simulations that follow the formation of individual stars and these galaxies. And what you're seeing here is sort of a kinematic map of a giant molecular cloud that's undergoing collapse. So these little bright points are these stars, and purple is sort of turbulent or non-turbulent gas, and orange is sort of very turbulent gas. And as sort of gravity and pressure compete, you will begin to see these stars form. And once stars form, they then exert feedback on their environment in the form of bipolar jets that you see going off. There's radiation from these H2 bubbles that will be expanding. There's also stellar winds going on. And if stars are massive enough, then they can eventually go supernova and destroy the entirety of this cloud. So this is sort of a video of one of our simulations. And what I do is I run these simulations, but I sprinkle dust in there, and now evolve the entire system with these dust grains that are live in the simulation. And so now we have this explicit dust dynamics that I told you about, but we also couple the dust to the heating and cooling dust terms that would happen, to the dust surface chemistry, and the radiative transfer that is in the cloud. So we try to do the dust physics as self-consistently as we can.
So the simulation without dust was MHD with radiative transfer of gas.
Yes.
And so what is like inherently different? Instead, you can't model each dust strain. So you collect them into like clustered groups of dust grains, and you assign each group mass and a density. So why is that inherently different from taking a lot of atoms and deciding that the region in space is a cell and it has a mass and density? What is different? So you have two species in a MHD radiative transfer simulation.
Yeah.
No,
that is exactly what we do. So the only change is like the previous simulations assume that the dust is glued to the gas, so you don't vary that parameter. And now it's a free sort of like the dust can move, and we see if that changes any of the conclusions that you find.
it's like a multi-material MHD radiative transfer simulation.
Yes.
Okay.
So to sort of jump into some of the stuff that we actually found that were interesting. So this is sort of the gas surface density of one of my clouds. And I'm zooming in around one particular star. And here there's sort of this particle distribution of the dust grains. And again, the gas surface density in the background. And by eye, you can sort of see that this overdensity of gas isn't really followed by the dust. And we could sort of look at this in a more quantitative manner and look at the dust to gas mass ratio. And here it's normalized such that the mean is white, and anything that is dust poor will be blue, and anything that's dust rich will be pink. And this sort of feature sort of jumps out where you see there's a dust deficit at the center and a dust surplus around it. So what happens is around the star is pushing this dust out from its vicinity, and this dust is then piling up in this region nearby. And it's roughly a factor of 10 reduction at the center near the star. And this is sort of one star, so we wanted to understand how does this reflect on the entire population of stars that we form in the simulation.
Sorry, in the previous plot, what are these sprinkling of orange dots there?
These are some of the dust particles that are in the region.
And on the right, it's a continuous density of particle. Like how do I connect? It looks like a zoom in, but I don't understand what.
Yeah, so here the background is the gas surface density, and then this is just the particles. And then here I divide the mass of the dust by the gas.
So those particles,
Smoothed out?
you smeared them out.
Yes, yeah.
That's very discrete distribution. Like
Is that all of the particles in the center one?
subsampling.
It's subsampling some of the particles at that region. Cool. Okay, so now if we want to look at the entire population of stars, one way, instead of looking at all these different zoom-ins of every star, we could sort of have a proxy for how much dust is near a star by checking how much dust has been accreted by that star over its lifetime. So this is sort of this ratio on the y-axis, so the ratio of accreted dust to accreted gas. So if there was not that much dust around you probably accreted less dust. And we're looking at this as a function of stellar mass. And here, this dashed line is what you would expect if all the dust dynamics are sort of glued to the gas. So you expect this to just be the mean of the dust to gas ratio is going to be the mean of the material that a star in this environment would accrete. So anything below it will be dust poor, anything above it, dust rich. And we could sort of look at our full physics simulation and plot this and then in terms of the stellar mass. So here, this is the interquartile and interdecile range of the distribution. And we see that at some stellar mass, the amount of accreted dust, accreted gas sort of drops very steeply. And to figure out what is actually driving this effect, we can turn on and off different physics in the simulation. And we find that once we turn off radiative forces on dust grains, then this trend essentially completely disappears, which sort of makes sense. Yes.
So stars themselves, they also produce dust because mass is lost from the surface. Do you take that into account when you simulate the amount of dust for different masses?
Yeah, so we don't take into account dust creation, but sort of the time scale for dust creation is much, much longer than the actual time scale of our simulations. So we'd sort of need these more evolved stars to actually start pumping out more dust into the environment.
Yeah, sorry, just on that point, do we understand that dust creation from the start?
Kind of, it's a very complicated process where you're like actually nucleating solid particles in a relatively diffuse medium. There's a lot of people that work on it. They have these like cool models of like if you have these little seed molecules and you see like other particles sort of form around them. But this is still like an active field where we don't exactly understand how all of these processes proceed.
So then the timescales argument is just an energetics argument?
It's just, yeah, it's like you need highly evolved stars. You also need to create all this material that is mostly like heavy refractory material. So you just need stars that are energetic and have the the material in the moon. Yes. Cool. So what's happening is you're pushing dust with radiation, and this dust is sort of evacuating these regions around these stars, and it's driving this sort of difference in the amount of dust that gets incorporated into these stars. And one other feature is also this huge distribution, even at a given stellar mass, of this ratio. And this is this is much larger than you would expect just from resolution effects or from the systematics in this simulation. So one question that we wanted to ask is,
did you consider also dust disruption? Because with massive star radiation could be very strong and the dust could be disrupted and the dust to gas ratio could increase also in methods.
So we consider sublimation, and the way we sort of model sublimation is the dust particle isn't taken into account in calculations if its dust temperature is high enough that this dust particle should have sublimated. So we do take that into account. Cool. So now if we look at this, we could sort of ask, is this real? Could this actually happen? Have people actually seen this? Because this is a lot easier to observe than this trend, because here you have to sort of look at the metallicity or the composition of stars that vary from maybe a few solar masses to several solar masses, which is relatively difficult to do. But this is at a given stellar mass, so this removes a lot. Yes.
Okay, sorry. On which part of the evolution do you measure those properties? Because I guess if you just slightly before everything is formed, it will be completely different than very initial stages, right?
Yes. So this is sort of a snapshot at the very end when we assume that all the stars have accreted, where all the stars no longer change their mass.
And there's no second generation fight for.
Yeah, no.
What is the meaning of above one? So without radiation, you have a very large region of accreted dust over accreted gas of above one. So a star is formed, you have its surface, and then there's a bunch of dust living on it without gas.
No, so one here is sort of normalized to the mean. So it's above the average that you would expect. So it just has a surplus of,
Expect from what?
Expect if the dust doesn't move. If you accrete the mean value of the dust to gas ratio is sort of that dashed line.
I was just wondering, why couldn't you go to, say, Orion, where there's lots of massive stars and also lots of low mass protostars, and just measure the metallicity as a function of stellar mass? Should show something like this?
My understanding is because your spectra change as a function of log, effective temperature and log G, there's a lot of uncertainty that is just added because of modeling that it makes it that it could blur a lot of these signals. So it becomes very hard because you could sort of
So what would be the fractional change in metallicity? That you're saying that's change in metallicity of the star is so small it's undetectable.
It would be point a few decks, so not undetectable, but relatively difficult to measure unless you have a large enough distribution and you can handle the systematics of measuring across stellar masses very accurately. Yes.
Sorry, I know you get bombarded with
No,
it's interesting stuff. So you've got this accretion kind of difference with stellar mass. Is that also borne out in terms of the size distribution that ends up getting accreted as well?
So we looked at this. There's not that strong of an effect. And the reason is because if you go through the force, so if you have radiation acting on a grain size distribution, and that grain size distribution is small enough, which a lot of these grains are, then you end up with a grain size independent effective acceleration. Or not effective acceleration, effective dust streaming speed. So essentially all your grain size dependencies cancel in that limit, so you don't get as much of a difference.
Okay.
All right. Okay. So let's go back to the sort of measuring different metallicities at a given stellar mass. So this begs the question of what determines what the makeup of the stars, right? So we expect stars that are born in the same cloud to be roughly made of the same material and to be very similar in metallicity. But there was this population of stars that were observed where their composition actually varies quite significantly from their neighbors. And this was sort of postulated like very early on. And the idea is that these stars are polluted and they are polluted by planets. And the reason the argument of planets was sort of made is if you look at the observations, here are sort of more recent observations of this variability in metallicity on the x-axis, and this is the cumulative distribution function. If you look at the axis in terms of how much this pollution would be if you convert this difference in metallicity to mass pollution. So if you now check if this was a planet, what would be the mass that it would have needed to be to give us that signal? And when you do that, you find that these signals mostly correspond to a few Earth masses. So this is sort of why this neatly fit the picture of, oh, maybe it's planets that are crashing onto the surfaces of these stars, depositing a bunch of material there, and that is what we're observing. But our argument when we looked at our simulations is that dust is essentially the same as planets. They're made up of exactly the same materials. Rocky planets are just very large dust grains. And because they are made of dust grains, right? So we said, okay, instead of having it be a single event where you're creating this very large dust grain, what if you accumulate all these dust grains throughout your lifetime, and this changes your metallicity, and we could test that by looking at the different statistics. So now we could look at two of the clusters that we simulated. So one is a smaller cluster, one is a larger cluster with roughly a combined number of thousands of stars. And you see that the signal that you would get roughly goes through the same limits as the observations see. So what this tells us is likely what's happening is a combination of both, right? You can get planets that crash onto their stars and pollute them. Therefore, this will happen. But you could also accumulate these differences in metallicities just from dust dynamics. And the fact that you are preferentially, some regions will be preferentially creating more dust, and some regions would be preferentially creating less.
What happens is not when you got this stellar mass observation. So you predict that most more massive stars will accrete less dust, right?
Mm-hmm.
So is the stellar mass observationally known? So you predict that there will be less dust.
Yes. It is not observationally known.
I'm sorry, this can be tested.
Huh?
It can be tested.
It can be tested, but there are there aren't observations trying to actually look at this as a function of stellar mass because it's more difficult.
So it's a clear test between the
Yes.
predictions.
Yes.
So what are these observations? Could you explain like these different orders? What did they do? For
Oh, the different observations. So they're essentially different samples. So this is sort of looking at a nearby open cluster. And this was looking, I think, at binaries and comparing different binaries and seeing the difference in metallicities. And I think this was also looking at some other clusters and the image are different.
so this is the kind of a distribution within a star cluster.
Yes, yeah. It depends on the exact study. Some of them will combine more than one cluster.
I'm extremely ignorant about this, but
what would I have to do to cook up a model that didn't go through those boxes? It has to go to 1 on the left-hand side. It's a cumulative df. It has to decrease monotonically. How would I get a model that didn't go through?
So you could get so essentially you just need to decrease here. So if your signal is too weak, so like you could sort of go through here and that's sort of a trivial result. So like if your dust is greater, you would sort of fall outside of the box, but you can sort of like, I guess if you're within the bounds, then you can always explain it, but it doesn't explain how large the signal is. So you're trying to explain both how large the signal is, and so like this really is the like outside of 0 is the part that really matters if you take the.
So should I not think about the left? How do I think about the white dashed box, for instance, Lu plus 2024? Should I only be thinking about the fit that's bigger than 0? What constraining power does that?
Yeah, so in a lot of these observations, what you can only measure is a difference in metallicity, so you don't have a sign. So one way of remaking this plot is like removing the sign from the simulations and then sort of having the boxes be narrow. But yeah. But the main signal you're trying to match is a few Earth masses at some given stellar mass. Cool. Okay. And one thing we could also do is now we know that this radiation can evacuate dust from around stars. Then if we put this dust around an even more luminous source, say an AGN, then that should be even more efficient at evacuating this dust. And we know that there's a lot of dust around AGN, particularly in the AGN pores. So this is sort of an idealized simulation that we ran where we had radiation MHD dust 3D simulations where we have radiation at this part of the box that is acting on the stratified dusty gas medium. And once you turn on the radiation, you see all these sort of features and wind go through the box. So you see dust and gas fluctuations and clumpiness that naturally forms when you have radiation acting on this dusty fluid and ejecting these very powerful winds. So this was sort of an argument that the AGN porous could also be the source of AGN winds that then couple on parsec scales to the galaxy.
So is that resolving the acoustic RDI?
Yes. Yeah. So sort of the clean modes you see earlier in the video, that is the linear phase of the acoustic RDI. Okay. So only, let me see, I'm going on. Okay. So here is sort of an analogy that I like to make for these instabilities, where if you sort of squint at both of these pictures, you will see that the structure that kind of forms in your cup of coffee is quite similar to some of this percolated structure that you see in the simulation. And it's because roughly the physics that is driving both of these things is very similar. You have some solid particles that are suspended in some fluid. And because of the different drag that acts on them, you'll have particles that sort of pile up, drag in more gas, and you create these pressure maxima that sort of drag in more and more particles and trap them. So you create this sort of filament-free structure that exists on many different scales for many different fluids regarding the exact dynamics of the system. So I like to do this with my coffee. But yeah.
Sorry, what particles are you putting in your coffee?
That does mean coffee. Yes. So I drink Turkish coffee, which has these particulates that are just the right size. Yes. Okay. Right. Okay. So now after we sort of talked about the dynamics and we let the dust particles move and we saw that they can move in different regions, I want to sort of ask, what effect does this now have on how the thermodynamics of star formations proceed? Star formation is very sensitive to temperatures and densities of the gas. And if the dust can change these properties, then you would potentially get different outcomes of star formation. And particularly, I want to talk about what effect the dust size has on the thermodynamics. So that is the main parameter that a lot of the cooling and heating terms depend on. So to do this, we sort of consider some grain size distribution. And we could start with this diffuse interstellar medium grain size distribution. And realistically, the way you want to do this is you would try to actually take into account what sets this distribution. So what sets this distribution is a balance of coagulation, which is grains growing, accretion, just accreting particles and molecules from the gas state into the solid phase, sputtering, which is grains sort of losing particles due to energetic electrons hitting them and breaking pieces off, and shattering, which is grain on grain. And the problem with this is to model all of these processes. These are happening at the grain scale, and our resolutions don't really capture that scale in the simulation. And to accurately try to model them, you would need very high, either high resolution or small time steps, and that's sort of very expensive at the given time for these simulations. So what we wanted to do initially is, would this even matter? Is this worth implementing in the simulations? So if you have different grain size distributions, does this affect your star formation in any way? So we looked at simulations that specialize in modeling these exact balance between the different processes. So in both of these simulations, these are linear models that start with some grain size distribution, take into account the parameters and very accurately integrate the grain size distribution you would end up with given the balance of coagulation, shattering, and destruction. And what they find is that in giant molecular clouds, you're in this very sweet spot where the gas is dense enough and cold enough that destruction is inefficient and growth is very efficient. So you would expect that the grains in these regions would be larger than we would see in the diffuse interstellar medium. The second piece of information is there are these observations called the Korschein observations, where larger dust particles are observed in scattering in these giant molecular clouds, which tells us that maybe you have larger grain sizes in these environments than, again, the diffuse interstellar medium. So sort of motivated by this, we consider the effect of increasing the grain size at a fixed dust mass. So we're holding the dust to gas mass ratio constant, but increasing the effective grain size in our simulations. And the main effect that we see on star formation can sort of be shown in this very simple cartoon. So say there's a bunch of gas that is on the right of the slide, and I have some dust in between, and this dust is very fine, so it has very high opacity, right? So if I have a bunch of photons that are trying to get through, it's very hard for them to access this reservoir of gas. However, efficient star formation, good. If I make these grains larger, then I'm effectively changing the total number of grains, and I'm lowering the opacity. So what I'm adding is I'm having this wall have now more holes that radiation could sort of propagate through and heat up this gas and have it be ionized and so on, and you would get inefficient star formation. So if we look at how this actually looks like in our simulation, so this is simulation with small grains, medium-sized grains, and larger grains than you would expect. And this is the UV radiation energy density. So so here, blue is sort of shielded gas, low radiation energy density. Red is very UV bright. So as we go to larger and larger grains, you see that around, and the purple points are stars that have formed in the simulation. So here you see that around these stars, you're now very UV bright, where before you were able to shield more regions of the gas from some of the more massive stars in the cloud. And this translates to changes in temperature. So now that cloud is also hotter, effectively. And more strikingly, if we look at the ionization fraction or the electron fraction in this cloud, so anything that's pink is molecular, anything that's blue is ionized, and you slowly see this cloud go from mostly molecular shielded gas that's cold into ionized hot gas.
So you have some constraint on the mass of the dust between the three options?
Yes.
Okay. What sets up?
So we just keep the total dust gas constant, which is sort of motivated by.
Yeah, I understand. So the mass is constant, and by changing the size, you basically reduce the density.
Yes.
But what constrains this total mass that you assumed? Why can't it be larger?
Right, so it's motivated by what drives the grains towards a larger size. So you have two modes of increasing the size of the grains. One is coagulation, which is roughly you take, like you could simply consider it, you take every dust grain and now stick it to its neighbor. So you've held the total mass constant, but changed the total number of the grains. And this is the mode that we think is most efficient in these clouds. The other mode doesn't preserve the total mass, which is accretion from the gas phase, where you're now adding more mass onto the particles, making them larger. So that is sort of why we did this experiment. But if you do it the other way, you would likely see different effects as well.
But these simulations didn't stimulate the creation of the dust grains.
No.
So, I mean, these simulations started from saying there is a constant mass. If I reduce the density, there is some effect on the whatever I would observe. But I could have the same density just by adding mass, because I didn't simulate how the dust grains were formed. So I can decide how they formed. I mean, if the simulation was so consistent on creating the dust grains, then I won't understand. But if the simulation started from dust grain sizes somehow, then so I don't know what option is right between these, because I can't infer if there was more mass. So
like these simulations aren't really trying to say this is what happens in a star forming cloud. It's sort of answering the question of if you have efficient coagulation, and that efficient coagulation shifts your grain size distribution in this way, this is how that would translate to the star formation. But ideally, you want to run this more self-consistent. So like now that we see that there is an effect, we would want to put in the models that try to now reproduce the same effect self-consistently, accounting for all these rates in the star formation.
The opacity is so strongly dependent on the grain size. You could probably add as much large grains as you want, and you'll never get back
Yes.
capacity to suppress it. So this is independent of how much mass you put in it again.
Yes. You could like
just got rid of the small grains, and that's what's good.
Yeah, because essentially your opacity goes as roughly the grain size squared, depending on the regime. But it's dependent on the dust to gas mass ratio linearly. So you sort of need to make that effect up with so much more dust. And even then, like these large grains don't really interact with the radiation very efficiently. So if you have dust grains, if you have larger dust grains, you will sort of have this effect. And we can now translate that to a star formation efficiency. So this is the total stellar mass that forms in these different simulations as a function of dynamical time. And we see that you make the star formation less efficient by a factor of 10. And to get a sense of scales, we could compare that to different experiments that other people have run. So Chung-Woo Kim down at Princeton and David Usanoff ran these simulations where they vary the metallicity, which is sort of the main lever that we have when we want to change star formation efficiency. Just to point out, the simulations by David are run with StarForge, so using that same exact physics and same exact models. And they find that if you vary the metallicity over a factor of 100, you only see a change by a factor of 2 reduction in the star formation efficiency. And this comes down to the fact that the grain size depends non-linearly or affects the opacity non-linearly. So you get more bang for your buck, essentially, as you change the grain size distribution.
Epsilon is just the max size of the polygon grains here.
Yes, yeah.
So what the key thing is not the shape of that spectrum, but the cutoff where.
Technically, both would. It would depend on both, because effectively what you're doing is integrating over the whole size distribution. But the importance is the efficiency of absorbing radiation changes, you change regimes as you go from small grains to large grains as well. So at some point, the slope doesn't matter. But for the smaller grains, the slope does matter. That gives you some different dependence on the grain size. Yes.
This also changed the conclusion from the previous part of the talk where by changing, you're effectively changing the relative amount of stuff that can start by changing like the
Yeah. So we check how that affects the earlier conclusions, and it's difficult to compare them apples to apples because you get different stars that form. So you sort of get a lot less stars in these larger grains, but from the statistics that we have, we couldn't find significant enough effect of changing the grain size on the metallicities.
You're showing us here the results of, I guess, in one simulation over 4 dynamical times that forms about 100 stars.
Yes.
If I run this now, this just seems like a very stochastic process. If I run this 1,000 times on some average, like how do I know that this is not just you picked one simulation and happened to do this? How do I know this is a general trend?
Yeah, so we test this with different, like, we don't have that many simulations, but we vary this with resolution, and we also vary the size of the molecular cloud. So we have small molecular clouds and larger molecular clouds.
Same trends.
And the same trends throughout.
What sort of observational constraints are there on this size distribution in these young regions? Do you get anything from like ALMA disks or?
Not so. ALMA sort of probes a very, very different regime. You have much, much larger grains at that scale. But it's very hard to actually see the grain size distribution because all these clouds are effectively opaque. One way that I'm trying to look at is these different temperatures and ionization fractions would change the chemistry. So you could potentially see different lines or different intensities that could then probe these. People are trying to probe it using scattering, but that's sort of, you have very high error bars that doesn't really give you a very strong, like, this is the grain size distribution in these giant molecular clouds. Yeah. Cool. Okay. And in those 5 minutes, I will mostly just show pretty pictures that I'm currently working on. So this is work that I've started since I've come to the Institute, which is now looking at how all these different scales of star formation couple to each other. So my favorite answer to a problem is throw more resolution at it, right? So star formation is this sort of process that starts at parsec scales with a GMC into clumps, and you sort of go into a stellar core. This core would form a disk, and then this disk would evolve into some planetary star system. So what we wanted to understand is what information does this system inherit from the larger scales? And how do you actually transport this mass and momentum and magnetic field across these 5 orders of magnitude? And how does that set the initial conditions, for example, of star formation and planetary formation, when we no longer have to run simulations that start from here and sort of impose different initial conditions. So here I'm just gonna quickly show this video that demonstrates the range of scale that we have in these simulations. So this is again from the star formation simulation, and this is zooming in around one particular star that will form in this molecular cloud. So we're sort of going down and trying to reach sub-AU resolution within a giant molecular cloud of that is 3 parsecs across, and this is sort of zooming in on the inner disk that forms in these simulations to try to sort of understand the structure, the sizes that you would get, and the magnetic field behavior in these simulations. And I'll quickly sort of show time evolution of this disk. So this will be over the course of around 20,000 years. So very short time scales for the giant molecular cloud, but you sort of see that this disk is changing very rapidly in time, and it's sort of changing as matter falls onto it, how much accretion actually happens versus how much mass stays in the disk. And if we look at it edge on, you can see where all, oops. So you see that they're all these material that come from all sorts of like angles that fall onto the disk and are sort of disrupting how the disk is aligned. So here the camera is sort of set so the disk is always edge on, but you see all this material sort of falling from different regions, which is quite different from our.
Did you fix the whole time,
Yes.
or were you?
Yeah.
Okay.
So if I keep the camera steady, you would see the disk essentially wobble as different angular momentum streams sort of fall into it and disrupt it. So there's sort of always some difference between the star and the disk angular momentum as both catch up with each other. But yeah, so I'll sort of leave it here and take any more.
Other questions, Nadine?
So yeah, I'm interested. It's probably these are already very expensive simulations, I imagine. Then you add in dust across a range of effective Stokes numbers, so marginally coupled, very tightly coupled. So how are you integrating the superparticles in this case in the tightly coupled regime?
So these simulations, as of now, do not have dust.
These
dynamics.
ones don't,
Yes.
but you're
Yeah.
only Star Forge.
The earlier ones?
Yeah, they're sprinkling in your dust. Yeah.
Yeah, so the dust actually reaches the streaming speed very quickly. So you don't end up having to really integrate it as tightly. So you could get these like at the resolution scales, the correct dynamics. If you really want to get the smaller scale dynamics, then it sort of becomes more expensive. But the dust dynamics alone isn't that much more expensive. It's mostly a resolution and memory effect that you are getting.
Okay, thanks.
Yeah. In these regimes, dust ends up being a lot more expensive because then it's a lot more tightly coupled.
Right.
And equations are more stiff.
More questions?
So there is initial conditions to all these simulations.
Yes, yeah.
Some distribution of gas to dust. Is there anybody who is trying to analyze where this distribution come from? So I have a GMC of some where these dust particles form get into this molecular cloud.
So there is a lot of work going into trying to model that. So we know that dust comes from two main avenues. One is from AGD stars, so evolved stars that are sort of have these dusty winds, or supernova explosions. And after sort of your top 3 stars, after the first generation of star formation, that is when you would expect dust to be present. So it's sort of, as you evolve with time, more and more stars die, you get more dust, but effectively settles at 1% on average.
From a supernova explosion, some particles stay on a millimeter scale.
No. So it depends on the region where different sizes can survive. But supernova are expected to have like a few microns to 100 microns particles that sort of condense out in the supernova wind. But that's highly uncertain. Like what the actual sizes are, we sort of think that supernova make larger dust grains, but it could be reprocessed in all sorts of different ways. So the dust you get in these clouds is sort of processed over like giga years into some effective dust grain that you get.
So in early star forming region, I would have a very different distribution of dust grains.
Yes.
Is there any signature on the star formation or the regions because there were no large dust grains in this model?
I don't think that is observed, but like one of the things people look at is like how would POP3 stars that are forming without like a lot of without metallicity, without dust, how does that change? Because we know a lot of star formation is regulated by the opacities that you have. So you have different expectations, but we haven't seen these stars, so we don't actually have a proper answer to like what really happened.
Okay. Any last question before lunch?
How should I think of those three different examples of very different size? The resulting stellar environment is going to then feed back on the rest of the galaxy. We know that affects. So should I recalibrate how I think about all these feedback descriptions that we're not considering this as an effect, presume?
So the way I think about dust is sort of like your messenger for feedback in a way, like radiative feedback. So you would expect that to change the efficiency of star formation in different galaxies. But how, on average, like if every single dust grain in that galaxy is somehow shifted towards larger dust grains, then star formation would look different everywhere in the galaxy. But it's likely to vary in different regions depending on different environments. So maybe on average, still end up with something that's similar. But there are people that are running simulations like this for galaxy formation and trying to understand how these changes affect larger scale observations.
Okay, we can track that in again.